In this lesson, we're going to take a very detailed look at how Michaelis and Menten derive their now famous Michaelis-Menten equation. So they looked at enzyme catalysis as a two-step process. So in step one was the reversible binding of the substrate, so forming what they called the enzyme substrate complex. So K1 here is the forward reactions rate constant, K minus 1 is the reverse reactions rate constant. So, and then step two, they view it as the catalytic step where the substrate was actually converted to product and released by the enzyme. And here, K2 is the rate constant for step two. It's sometimes called K catalytic or KCat for short. FYI, we'll see that again. So couple things we need to talk about before we dive headlong into our derivation. So you can kind of see here that the enzyme exists as free enzyme before and after the reaction and as the enzyme substrate complex in the middle of the reaction. And those are the two forms the enzyme is going to exist in. And so we can derive an expression here for the total enzyme concentration. So that just says it's equal to the sum of the free enzyme concentration as well as the concentration of the enzyme substrate complex. So the reason this is important is we're going to use it to derive an expression for the enzyme concentration here. So here total enzyme minus ES, and we're going to use that during our derivation. The second thing we'll look at is if you look at the second step is really the catalytic step, and it is what really determines the velocity of the reaction. The velocity of that second step is the velocity of the reaction. And so the rate law for that second step gets us our velocity for the overall reaction here. And so it's just the rate constant K2 times the concentration of the reactant in that step, which is the enzyme substrate complex. So, and the reason we're bringing this up is twofold. One, we're going to come up with an expression for the ES complex concentration that we'll use later. But two, we're going to come up with an expression for what we call the maximum velocity. So this reaction is going to achieve a maximum velocity when all the enzyme is tied up as enzyme substrate complex. So when our total enzyme concentration is all enzyme substrate complex, that's when we'd reach the max velocity, and that's what our second step's rate law would ultimately turn into. So now we've got an expression for the max velocity, Vmax, as well, and we'll use that in our derivation as well. Finally, on to the derivation proper. So the basis for Michaelis-Menten's entire derivation rests on what we call the steady state approximation. So, and the idea is that we're going to achieve some sort of steady state where the amount of ES complex here is going to be constant over time. So it's no longer going to be changing. And the idea is that any reaction in which the ES is produced and any reactions in which ES is consumed, those rates are going to balance perfectly. That way the overall concentration is no longer changing over time. So we can see that the ES complex is being produced in step one, but it's being consumed in the reverse of step one, as well as being consumed in step two. And so the rate of the forward step one has to be exactly equal to the rates of reverse step one and step two added together. So if we look at the rate law for step one, so it's just the rate constant K1 times the enzyme concentration times the substrate concentration. If we look at the rate law for the reverse of step one, it's just K minus 1, the rate constant, times the enzyme substrate complex, which is the reactant for the reverse reaction. So, and then finally the rate law for step 2. So the rate constant K2 times the reactant in step 2, which is the enzyme substrate complex. So, and in this case, we can derive our expression for the steady state approximation that the rate at which ES is produced is equal to the rates at which it's consumed. And this is our steady state approximation. First thing we're going to do here, though, is we came up with an expression here for our enzyme concentration, and we're going to substitute that in right here. We'll copy the reaction over. Cool, I've substituted that right in, and now we've got a new expression here, having replaced the enzyme concentration with the total enzyme minus ES, again, that we brought up right back over here. Next thing we want to do is collect all the rate constants on the right-hand side of this equation. We can see that K minus 1 and K2 are both multiplied by the enzyme substrate complex. In order to get K1 off to the other side, it also needs to be multiplied by the enzyme substrate complex concentration. So, and what we're going to do is actually multiply by the enzyme substrate complex concentration all over itself. That way, effectively multiplying by 1, we haven't really changed the equation. But now we can see that every term in this equation actually has ES in it, and they all can cancel, just divide it out. So, and from here we can see that we can actually now divide through by K1 and have all the rate constants on the right-hand side of the equation. That's going to leave us with the following. Cool. It was this combination of rate constants that Michaelis-Menten referred to as the Michaelis constant, Km. So if we rewrite this equation with all of this now being Km, cool. From here, we're going to multiply by ES, and we're also going to distribute the substrate concentration through what's in parentheses there. So from here we can see that this term has an ES concentration in it, so does this one. We're going to combine them on the same side and factor that ES concentration out. Now we'll divide through by Km plus S to get an expression for the ES concentration. I'll continue that on up here. I'm just going to flip everything around as well. From here, we've got a equation equal to our ES complex concentration. And if you recall, we came up with an expression for that ES complex. We're going to substitute that in right now. So now we're going to have V over K2 equals your total enzyme concentration times S all over Km plus S. Cool, and if we multiply the K2 up to the other side, so, and if finally, if you recall, we came up with an expression for Vmax, and Vmax was equal to K2 times the total enzyme concentration, which is what we have right here. And we're just going to substitute Vmax in right for it. Cool. And now we've derived our lovely Michaelis-Menten equation proper. So how we use it comes up in the next lesson.